So our application question yesterday, that was about cookies. That was your intro to linear programming, which is what our lesson is today, and it is our last lesson. So today, we're going to be walking through those questions. They do take a bit. Some of the questions, though, you'll find, and this happens on your test as well, there's no context to them, and I already gave you all of the things, like the constraints and profit function, so you don't have to do a lot of work. But the granddaddy problem at the end, where you have to do all the work, that would be the hardest thing that I could ask of you. And that is what is on a good chunk of your homework assignment tonight. You'll notice your homework assignment is out of the book. 1, 2, 3 questions. 3 little questions. And you're going to want graph paper to do them, and you'll see why as Mrs. Abruzzo struggles through her attempt to graph.
Graph paper? That means it is not a little question.
Just your graphing is so important. You'll see what I mean by today, because you're going to watch me graph, and then you're going to be like, oh, that poor lady. Okay, so this is what it looks like to be a feasible region and have feasible solutions. Your solutions occur anywhere within that region. Now, that's a really weird-looking region. We're not going to graph anything that looks like that. But if I'm trying to maximize or minimize profit or cost in an application question, those values would occur at what are called the vertices, so the corners of the feasible region. And we saw that kind of yesterday with the cookie problem, so more of those. This is a little misleading. It says step 1 is to graph. Not normally. Usually step 1 is to create the constraints that then you graph. And then you find the corners, and then you plug them into the objective function. So just look, 3 little steps. That's it, right? All right, let's take a look at number 1. This is a question, man, it looks like it was taken straight off your test on Friday. I give you the optimization function, or the objective function. These are the constraints, okay? So we're on worksheet 11. There's an I right in there. The constraints are what you're actually graphing. So these bottom 2 constraints are what we like to call the obvious constraints in the real world questions. They're saying your X's and Y's have to be positive. So like we saw the cookie problem yesterday, like you can't make negative boxes of cookies. So automatically you were restricted to the first quadrant. But let's talk about graphing these other constraints. So if these were in slope-intercept form, I'd be a lot happier. So your first issue is, can you do a little rearranging for me? Get this so Y is isolated so I can graph a little more appropriately, because you know what my graphs are going to look like. So here I'm going to subtract the 2x over. We're going to get Y is less than or equal to negative 2x plus 10. And then similar moves here, guys. We're going to subtract the x and divide by 2. So you're going to get Y is less than or equal to negative 1/2 x plus 4. And you can show as much work on that couple steps as you need to show on your homework. If you're not real good at isolating without making mistakes, like show extra steps. All right, so now here's the fun part. We got to graph this. So we're already restricted to the first region, but now I need to graph this inequality as well as this inequality. So I'm going to start up at 10, and then my slope is down 2 over 1. And you know what's going to happen when I go to draw this line. It's going to be awful. So if you were on your homework or now on your notes, you guys should maybe use the edge of your calculator case to use the straight edge. I'm just going to wing it. Aw, jeez. I was so good for like the first 3 points, and then whoops. Now the other line, this guy, that starts at 4, and then his slope is negative 1 over 2. Close enough. And then the feasible region would be, remember, we're shading underneath all these lines, these red and green lines, and then to the right and above the axes. So this right here is your feasible region. So now what you got to do is listing me out all of the vertices. So the corners, and I didn't graph the lines really well, but I graphed my points really well, so I actually can tell where this ordered pair is right here, I think. If I couldn't tell where that ordered pair was, I'd have to come back and do a little algebra to figure out where they intersected. But I'm pretty sure we have a vertex at 0, 0, at 5, 0. This guy appears to be at 4, 2, but you guys have a better picture, so tell me if I'm wrong. And then this one is at 0, 4. So our maximum and our minimum occurs at one of these values. And the way we find the actual value is we take these critical points, these vertices, and we plug them into the optimization function, the objective function up here. So plugging in a 0, 0 here, you got 3 times 0 minus 2 times 0, which gives us 0. All right, that's probably not going to be anything exciting for a maximum. All right, plugging in a 5, 0, we get 3 times 5 minus 2 times 0, which is a 15. Good. All right, plugging in a 4, 2, you get 3 times 4 minus 2 times 2, which is 8. And then plugging in a 0, 4, you got 3 times 0 minus 2 times 4, which gives us a negative 8. So the question, the directions up here say find the minimum and the maximum, both. So here we go. This is, oh geez, I just crossed it off. Whoopsies. There's your maximum, and here is your minimum. But that's not good enough for like an answer. So you're going to write me something over off to the side here. You're going to say that we have a minimum of negative 8 at the ordered pairs 0, 4. And then a maximum of 15 at 5, 0. This is the actual solution. So that question, which will show up, you know, homework on your test on Friday and also on your post-test next week, is just simply, if I take all the story problem aspect out of it, can you create the feasible region, find the critical points, and tell me the max and min? But then, of course, we got to throw some other stuff into this question. These are a little boring. Like, you almost crave a story problem at this point, don't you? If you don't mind, I would like to skip 2, and I'd like to look at the next example, which is a story problem. So we're going to ease you into this a little bit, guys. This story problem is pretty much done for you on a lot of parts of it. We have a leather company that wants to add belts and wallets to its product line. The belts require 2 hours of cutting time and 6 hours of sewing time, and wallets require 3 hours of cutting time and 3 hours of sewing time. The cutting machine is available 12 hours a week, and the sewing machine is only available 18 hours a week. And belts will net $18 in profit, and wallets will net $12 in profit. So what I like to do right away in these questions is define the variables, which they already did for you. They said let x be the number of belts and y is the number of wallets. Let's go ahead and get the objective function out of there so we don't have to think about these numbers anymore. These values are going to help you figure out the objective function, which helps us find profit later on in the problem. So $18 for every belt and $12 for every wallet. That is the objective function. We will come back to that at the end of the problem. So on this question, and this very much looks like kind of what you're going to see in your test. So we're kind of leading you through it. We went ahead and gave you the obvious constraints where it says x is greater than 0 and or equal to 0 and y is to be greater than or equal to 0 because you can't make negative belts and wallets. Or at least we don't want to consider what happens when you make negative belts and wallets. So let's talk about the constraint that is given to you because of the cutting machine. The cutting machine is going to limit how much product you can make. So a belt requires 2 hours of cutting time, and a wallet requires 3 hours of cutting time. So 2x plus 3y, and the cutting machine is only available for 12 hours. So that's why it says already less than or equal to 12. So now you can set up a similar constraint because of the sewing machine limiting you. So a belt needs 6 hours of sewing time, and a wallet needs 3 hours of sewing time. And it's got a up to 18 hours thing going on here. So what did I just say? 6x plus 3y, and then it's up to 18 hours for that machine. All right, now normally nothing would be done for you and you guys would have to graph this. But if I flip to the next screen, I noticed they already graphed it for me. So that was very kind. But let's talk about what I would have had to have done in order to graph this. The cutting time inequality and the sewing time inequality, you would have wanted to rearrange both of those into slope-intercept form more than likely. So maybe you rearrange them into, let's see, this guy we would subtract the 2x and divide by 3. So negative 2/3 x, and then remember you divided everything by 3, so plus 4. And then the sewing machine constraint, let's see, we'd subtract 6x and divide everything by 3. So that would be a negative 2x plus 6. So if I was having to graph this by hand, I always revert back to a slope-intercept model of graphing because my graphs are so horrible. Now, the other thing that they've already kindly done for you, besides the graphing, they've also found a point of intersection for you. That's not very easy to find by looking at, especially my graph, because you know my graphs are never, like, correct. So if we were doing this one completely by ourselves, without them just telling us the answer there, you would have had to figure out where that red and blue line intersected. So you either would have found the solution to this system or this system. So like if you used this version, you could use elimination to solve it. And if you use this version, you would use substitution to solve it. So you kind of just decide which method of system solving you like the best. Most of you like elimination the best. So you would have done a little elimination work. Now I know you're looking at this going, what do you mean? It's not equals. Like usually we just do systems with equations. Well, you just pretend it's an equation. So like for instance, right here, if I were to hit this guy by a -1, wouldn't that knock out the y's? So we'd end up with -4x equals -6. And then this is what happens. You end up with 6 divided by 4, or 1.5, which is exactly what they got, right? Then they plugged it back in and found y. We'll talk about that answer in a minute. Because remember, this is a real-life question, so we'll come back to that idea. Either way, they did the work for you. They found your 4 vertices, they plugged them into the profit function, the optimization, or the objective function, and they found the results, and they said, boom, there you go. Your maximum profit is 63. If you were to create 1.5 belts for every 3 wallets. Okay. So I don't necessarily know that that means we are going to make exactly 1.5 belts, because you can't, and exactly 3 wallets. I think they're just saying that's the ratio at which you produce them. So maybe, I don't really know anything about this. It depends on how many workers they're going to have working or how many machines they decide to do, but that's the ratio at which they should produce belts to wallets. Well, yeah, it's a silly looking question. And I know you're like, people don't really do that in real life. No, they don't bust out their graph paper and create linear inequalities to bring to companies, because there's a lot more intricate math involved, right? Worker laws. How often do they need breaks? Some of your workers work more productively than others. How many machines do you have going? How many machines can you possibly have on your floor space? Is there a point at which you have too many machines and not enough workers, or vice versa? So there's a lot of components to real life industry that they have to consider when the person comes in and does analytics on this company. And it doesn't involve a piece of paper and a ruler. So just remember that.
It does?
It does not involve a piece of paper and a ruler. It involves much more intricate math and usually computer programs. Always computer programs. So,
Computers are better than
well, but people program the computers for efficiency, right? Yeah. So, no or multiple optimal solutions is an option. Sometimes you guys will have what's called an unbounded region, where like it just kind of goes off forever, and you wouldn't have a maximum in that case. That usually doesn't happen in real life because there's always something constraining your math. But once in a while, the PreCalc book throws a question that's an unbounded region. The other option, and we're going to see this in the next 2 examples, I think, are where maybe you have more than one optimal solution. Like we saw that yesterday with the cookie problem. They could have created 2 different scenarios where they maximize their profit, and it was up to them to choose. Do you want to make like 30 boxes of plain cookies and 40 boxes of icing? Or I forgot what they came out to. But something like that. Either way, it gave them the same profit. So on the back of worksheet 11, we have this example that's kind of mostly done for you. Didn't have any story problem to go with it, but they had an objective function right here. And then they had some constraints, and they graphed it for you. So that was very kind. Not only did they graph it for you, they also found the points of intersection, so yay. And now they're taking each of these vertices, and they're plugging them into the objective function. So we can do that. They kind of halfway did that for us too. So 6 times 0 plus 3 times 0 is 0. And then this would be 12 plus 12, so 24. This would be 18 plus 0, so 18. This would be 0 plus 12, so 12. And 18 plus 6 is 24. So here's an example. If they want me to, they just want a maximum on this one. So if they want me to find the maximum, well, the maximum value of whatever they're doing here comes out to a 24, but it occurs at 2 different points of intersection. So the maximum occurs at 2, 4, or 3, 2. So this problem has multiple optimal solutions. If you ever in your life remember that phrase for multiple optimal solutions, I give you a high five. Okay, that's the fancy way of saying it. All right. Moving along. This one is, man, I really messed up the graph last hour on this one. Let's see if I can do better this time. So there's no story problem associated with this question. It's just straight up, here's your objective function and here's your constraints. So objective function, 2x plus y, we'll come back to that at the end of the problem. The constraints are the things that we have to graph. So, this guy. Before you graph it, you're going to want to rearrange it, right? So y is less than or equal to negative 2x plus 11. The rest of these are pretty boring lines to graph. They're either horizontal or vertical lines. So that's good news, I guess. I'm going to start by trying to graph this, and I'm going to try to do it better than I did in first hour. Those poor kids in first hour, they get the worst graphs. All right, down to right one. Yep. Oh, geez. Okay, pretend. So the other constraints, let's talk about these. Y is less than or equal to 5. That would be this guy. Horizontal line at 5, shading below it. We'll come to the shading in a minute. Y is greater than 0. That's just the axes. X is less than 5. That would be right here. And then greater than 0 would be here. So the feasible region that we end up with is this thing. And this is where, I don't stand a chance of seeing where this intersection point is. So we're going to use some algebra to figure out that intersection point, but methinks I got the other ones. So I'll give you all the silly lame ones. So, 0, 0, which everybody knows is, if this was a real life question, that would not be our answer. I believe this one, you know what, guys? I can't really read what I have anymore. Is this at 5, 0? Okay. Did a little too much scribbling. All right, this one's at 0, 5. I think this one's at 3, 5. Can you confirm that for me? Your picture looks way better than mine, so. Okay. And if we weren't sure, we could set the lines equal to each other or do some substitution to figure out, which I'm going to have to do on this one. Now, this particular intersection point, it's where my red line intersected the vertical line of x equals 5. So in order to find that value, I know the x value is 5, so I'm just going to plug that in real quick. So negative 2 times 5 plus 11, that came out to a 1. So I don't know if your picture was really beautiful and you already figured that out, but I'm seeing an intersection of those two at 5, 1. So those are all of the possible values for which my maximum and minimum could occur. And now we go and plug into the objective function. So 2 times 0 plus 0 gives me 0. 2 times 5 plus 0 gives me 10. 2 times 0 plus 5 gives me 5. 2 times 3 plus 5 gives me an 11. And then 2 times 5 plus 1 also gives me an 11. So this is another case where there's more than one optimal solution for a maximum. And then the minimum is 0. And they want both the maximum and minimum. So we say you have a minimum of 0 at 0, 0. And then you have a maximum of 11 at 3, 5 and at 5, 1. So that was a case where we had multiple optimal solution places. All right. So far, so good? Let's get some story problems. That's where the real excitement comes in. This one's about roller skates and ice skates. This is like the second question we've had having to do with ice. Oh no, the other one is figure skaters. That's what it was, right? Figure skaters on the last one, like yesterday. Okay, so, wow, this one has like nothing. However, they did give you some nice information put into a table. So that's helpful. And the other thing I should notice about this question is they did define your variables. They put roller skates on the x-axis and ice skates on the y-axis. So you might want to make a little note to yourself in your chart that roller skates are x and ice skates are y. Okie dokie. First, they want me to write an objective function. Let's get these numbers out of the way. These are the profit numbers that they make. And you can call your profit function whatever you want. I like to call it like P of XY. Like instead of F of XY, just P stands for profit in my head, so that's why I go with that. And then $30 for every pair of roller skates and $40 for every pair of ice skates. We're going to come back to that objective function later.
Is it pairs or is it just one skate?
Oh, I don't know. They're not real specific about that. Let's assume they mean pairs. Otherwise, that's kind of weird. I don't know if they'd make skates singularly. Maybe they do. I have no idea. Okay. So they want me to write my constraints, and I write too big, so I'm going to write them down here. There's some obvious constraints. Like you can't make negative skates. So x has to be greater than or equal to 0, and y has to be greater than or equal to 0. And then there's some constraints based on the time it takes to assemble and also to package and check for shipping. So let's talk about this first row of information about assembling. So 5 minutes for every roller skate or roller skate pair, whatever they're referring to, and then 4 minutes for every ice skate. And they have up to 200 minutes available in their time. So less than or equal to 200. And then similarly, you're going to set up another constraint based on the amount of time it takes for them to check the packaging. So 1x plus 4y, and then up to 120. All right, so if I was going to graph this, which apparently I need to graph it, there's no way I'm going to be able to graph even close to accurately unless I have it in slope-intercept form. If you guys want to use the intercept method of graphing with standard form, you're more than welcome to, but you're pretty much guaranteeing that you're going to have to use more algebra to find the point of intersection when you do it that way, which is fine, because frankly, I have to do it that way anyways. So here, we're going to subtract 5 and divide by 4. So y is less than or equal to negative 5/4 x plus 50. And then this one rearranges into subtract the 1 and divide by 4. So negative 1/4 x plus 30. Thank you. All right, so the first quadrant is where we're limited to. They kind of already sent me in the right direction there, so that was nice. Let's talk about these red inequalities, though. This guy first. So it starts up at 50, and then we're supposed to go down 5 and right 4, so that doesn't really take me anywhere but to the axes. Hey, that was almost a good line. Look at me. All right, now the other line, which I'm going to call the blue line so I don't get confused in a minute, negative 1/4 x plus 30. Yeah, this is where, I don't care how good of a grapher you are, you probably don't know where they intersect. But here's my feasible region. Okay, so this guy and this guy and this guy are obvious vertices. This is the one I don't know about. It's not 2020, but that was a good guess. Oh, it is 2025. Did you get that from algebra or from just visualization?
Yeah, I'm really good at graphing.
You are really good at graphing, because I don't even think mine's even close to that. All right, so 0, 0, 40, 0, and 0, 30. And then Daniel already figured out where that intersects. Good on him. I don't stand a chance of figuring out where those intersect without some algebra. So what I'm going to do is I'm going to go back to my blue line, red line. And I got to choose whether I want to solve this through elimination or substitution. So you guys choose for me. I don't really care. You want to do this one through elimination or substitution?
Substitution.
All right, so substitution says I would set these equal to each other. So negative 5/4 x plus 50 intersects with negative 1/4 x plus 30. That was kind of a weird choice, Daniel, because now I got fractions. You know how I feel about fractions.
Well, the fractions cancel out.
All right. Kind of, yeah. Yeah, they do.
So that's 1x.
You're going to bring them to the right? Which way do you want to go?
I don't care.
Okay, so if I add the 1/4 x over, you do get negative x, and if I subtract the 50 over, you get a negative 20, and this. Yes, indeed, you get x equals 20. And then if you plug that back into your favorite equation, literally anywhere in the problem, for this one or for this one, you get 25. So now we got to go back to our profit function. We got to plug each one of those into our profit function. Well, it's not 0. If you plug in a 40 0, we get 1200. If we plug in a 030, we get a 1200. But if we plug in a 2025, I believe we get 1600. Could someone double check that for me? You finally get your calculator out.
I figured somebody else was going to do it.
Someone is. They're just waiting for you. It is 1600. Okay. So that was a fun activity. Okay, how many roller skates and ice skates should be manufactured to maximize their profit, and what is the maximum profit? So we have a max profit of 1600 when we produce 20 roller skate or roller skate pairs, we're not really sure what they're doing here, and 25 ice skates. Can you read anything I just wrote? Gosh, you know how ironic it is that I sit there and yell at my 9-year-old daughter for her horrible handwriting? And that's what I come to work with.
My dad used to.
Isn't that awful?
For my camera.
Such a hypocrite, you, a bruiso. Okay, could you guys find worksheet 13 next? Yeah.
Is like the optimal number to sell always the vertice closest to y equals x?
No. It depends on what your profit function is, because sometimes there's a negative component in the profit function. I mean, in real life, the way our problems come out too, yes, they're like usually the one that's kind of off to the side here, but sometimes it's the top one. So it just depends on what the optimization function is. And because we make these up, they really don't make any sense. It's not like we went and like interrogated someone at a manufacturing facility and we're like, how many roller skates do you make? Yeah, we just make these up. They're not based in true life. Apologies, kids. Did I just really like make you sad?
Yeah.
Wouldn't that be cool if I could spend my summer like working and finding real life applications?
You should do that.
I did with my dad's work. I ended up having him like write up some stuff and some really cool things, and it was neat. Turns out a little too elaborate for the curriculum at the time, you know? Like, you guys haven't been to college yet. So the work that an engineer goes through, like, very little of it are you going to understand the math behind of it yet. You are capable, yes, but like as an introductory math lesson, not the best moment. So, in an effort, just teach you the calculus. There's actually I shouldn't say very little calculus in engineering. Depends on your type of engineering, but I asked some engineers, depending on your type of engineering you're in, and like what actual math like, do you feel is what you rely on the most at this point? And it's geometry. Yeah, which makes sense. But these were elder engineers who were like, everything that they did was by hand for many, many years, so that's what they rely on. The newer generation, right? So we used to have a drafting table in our basement. It was like the coolest thing, you know, as a kid. We're like, this is so cool. Really antiquated now, but it was cool back then. But, you know, the newer generations coming up, it's so much more automated and technical on the computer side of things. So everything's kind of different.
I don't even need the real calculus.
That's not what I'm saying. Hey, Mr. Aeronautical engineering? Is that what you're going into? Yeah, you're going to need calculus. Sorry, buddy. Nice try, though. Nice try. I don't need a calculus. You're going to need a few things beyond calculus, sir. Nice try, though. I have it right here. What am I doing? 13. I want to look at number 7. Number 7 is a fantastic question to get you going on worksheet 13. You have a few problems out of page 410, which I will post about an hour from now. And then you guys are going to do a couple problems off of worksheet 13.
Didn't you say that like the hardest course that you took in college was like analytical geometry?
Yeah. It wasn't hard. It was just like obscure and like way out of left field for me because I literally had we don't call PreCalc this, guys, but PreCalc is analytical geometry with trigonometry. Like, that's what it is.
No, analytical geometry.
So, like, when we start talking about the conic sections and things like that, that's coming up next semester. So, analytical geometry, I'm you guys take a course of geometry and then you're kind of like, and you're done. So applied geometry is a little different. But one could argue trigonometry is geometry, and various parts of algebra are in geometry as well. There's a lot of infusion in math, especially at the high school level. You guys are finally dipping your toes into big kid math, right? Finally.
This is just now big kid.
Yeah, it kind of is.
Felt like
And
big kid math for the past 3 years.
well, and it's hard because, like, you know, people who don't enjoy their math experience, let's say, and they just can't wait to get out of it, like in general, you don't need to agree to any of it.
Yes.
That resonates with me. You know, they ask the question of, like, why do I need to know this? And it's like you, a particular child who, like, never is going to use math again in your life, like, maybe you don't need to know it. But, like, at the Algebra 2 level, my argument to them is, like, I just want you to get a good score in your SAT test, and guess what your SAT test encompasses? All of Algebra 2. So, you know, then you get the sassy pants who's like, well, I don't care about my SAT. And then, like, what do I say to that kid, you know? Sorry.
Yeah, I don't care.
I do care. I care deeply. I care that you don't care, I guess, is what I care about. All right.
But you don't care that they don't care.
I
There's no
do.
reason for you to care if they don't care.
I do care, though. Isn't that sad? Keeps me up at night. Anywho, Mr. Big and Miss Smalls. Why can't she be Miss Big? This is sexist. I don't like this. All right. She's starting a company.
Didn't you write this?
I didn't write this. This was written in like the 90s. I wasn't even a student here yet. I could tell from the text. That font, that's not even a thing anymore. Yeah, vacuum. Remote control vacuum. We got Roombas now, people. We don't need that. We need to update this question. Okay, they will make big vacuums and small vacuums. Remote control vacuums. What? Okay, they only have materials to make at most 6 big vacuums and at most 8 small vacuums each day. And it takes them 2 hours to assemble a big vacuum and 1 hour to assemble a small vacuum. And they only have up to 16 man hours to put in. Why not woman hours? I don't like
Why
this.
is it only 16 though?
Shifts. Maybe they have 2 8-hour shifts or something. I don't know. I didn't make up this problem, man. They're simplifying the real life components to this. There's a lot of things that go into this besides, like, 16 hours of work. Boom.
Because, like, if you have 2 8-hour, that's assuming you have 2 employees, right?
I guess. I don't know.
Right?
It's Miss Biggs and Miss Smalls.
And based off of how many employees you have, right? So, like, if it's an 8-hour shift and you have 20 employees,
I guess it's just them working.
160
It's this
hours.
dynamic duo of Mr. Big and Miss Smalls, and they're assembling these vacuums. I guess.
Terribly inefficient.
They really should figure out how to... Yeah, I'm with you. Okay, so the profit is $120 on the big vacuum and $100 on this... What are they charging for these vacuums? That's a profit, though. Goodness. All right. So that's the objective function right there. The profit function is 120... Ooh, we didn't define variables. Who do you want to represent as the X?
B.
The number of big vacuums?
Oh, wait, X is the number.
Yeah, and then Y would be the number of small vacuums. So with that in mind, we would call this 120X plus 100Y. We're on worksheet 13, side B. So that's the profit
What's up,
function.
boys?
What's up, toys? That's your homework you did last night.
I didn't.
Uh,
I wasn't even here yesterday, so I have 3
but
days
you
to
watched
complete
the
it.
video. What? He's just talking gibberish right now. That's adorable. I wasn't here yesterday, so I get 3 days to complete it. That's not even a rule.
That's in the student handbook.
That is not a
It is
rule.
too. I read the entire student handbook last week. Why? Because I wanted to know.
Okay, let's talk about our constraints. The very first one says we can only make up to 6 big vacuums. So big vacuums has to be less than or equal to 6. That's what I know.
That's what I did instead of doing my homework.
Uh-huh. The small vacuums, at most 8. So Y has to be less than or equal to 8. And then the last constraint has to do with amount of time available. So 2 hours to assemble a big vacuum and 1 hour to assemble a small vacuum. So 2 hours for a big vacuum, 1 hour for a small vacuum, and they can throw up to 16 hours in. So less than or equal to 16. And now we're all in for a treat because I'm going to try to graph. Okay, so yeah, it's a little hard to read. At least there's marks along the axes, right? I'm going to start by rearranging this red one because I can't handle that. I'm going to subtract the 2x over, and this becomes y is less than or equal to negative 2x plus 16, which means I got to go all the way up to 16. Great. 1, 2, 3. I don't know if I miscounted. It doesn't matter. All right, and then whoop, we'd move down. It would intercept the x-axis at 8. Because if you set a 0 in for y, either version of this, if you put a 0 right here, you'd get 2x equals 16, so x equals 8. I just found the intercept through the standard form method. I knew I was a lost cause when it came to graphing, so I didn't really bother to graph real accurately because I knew it was not going to go well, clearly. So the other things that they have restricted us by were that x has to be greater than or less than or equal to 6. So like here, oh man, I can't even graph a line anymore. And then y has to be less than or equal to 8. Lovely. Okay, so this thing. This is my feasible region. Wow. Here, and here, and here, and something's going on here, and here. Now, I noticed on your paper they had 4 ordered pairs, and I see technically 5 vertices. I think they're implying that we're all good enough at this by now to realize you are not going to maximize your profit by making nothing. So they're not even going to consider the 0, 0 as one of our critical points. So let's talk about the other critical points we have. I believe this one's at 6, 0. And this guy's at 0, 8. And the other 2, I didn't even come close to graphing properly, so I'm going to have to do a little bit of algebra to figure out what's going on here. So this ordered pair right here is where the x value is a 6. So if I could just plug in a 6 into either one of these red versions here, like right here would be fine, that would end up being a 4 for my y value. Now this intersection point, that's where the y value was an 8. So again, I could go to either version of my equations here, but if I plug in an 8 for my y, I end up with 4, I believe. So now I would go back and I'd plug all those into my profit function, and I just want to find the maximum profit for them. I'm going to need y'all to do that for me. I'm guessing it's at either 6.4 or 4.8, and I'm pretty sure it's at 4.8, but could someone confirm that for me? Awkward sound. What is it?
1280.
Okay, thank you. So maximum profit of 1280 when they make, for big vacuums, I never spell vacuums right, so I just go that, and 8 small ones per day. Good luck, Mr. Big and Ms. Smalls. All right. And to you, children, good luck as well. So on this worksheet, if you flip to the front, you guys are assigned numbers 2 and 3. We're on worksheet 13. So number 2 and number 3. And then on page 410, I believe you were assigned as 3 little baby problems, 9, 12, and 29. And these should be done on graph paper. So before you leave me, please, please, please grab graph paper off the back table. All right, that was it. That's our last lesson. Woo! I'm going to stay home from now. Good luck, children.